Welcome back to the formulaic approach. In today's video, we are going to be covering the alkenes, just like we did of alkanes. The link to each video I'm going to leave in the description. Today we are going to be talking about the alkenes. We are going to be covering what they are. Okay, we're going to cover what they are. Then we are going to talk about their composition or general formula and basically their structure. We'll talk about their structure. We'll talk about their mode of preparation. And we'll talk about their physical and chemical reactions. Physical and chemical properties. So these are the things that we're going to be covering in today's video. But stick with me till the end, because just like I did in the former video, I'm likely to still engage in some mechanisms of reaction so that you are going to understand the way some of these things proceed and some of the reactions that you already know in some cases, the way they proceed. So the video is going to be for you even if you already know a little bit about alkenes, because I'm going to go do some mechanisms, okay, so that you can also learn something more. All right, now let's talk about what alkenes are. Now generally alkenes are called they are commonly called olefins. Okay, olefins. They are a group of unsaturated hydrocarbons. Now they are a group of unsaturated, which could be cyclic or acyclic hydrocarbons that have the general formula CnH2n, so which is 2 hydrogens less than the alkanes, right? Each alkene is going to have 2 hydrogens less than the corresponding alkane, okay? So they are unsaturated, having the general formula CnH2n, and they are sp2 hybridized. So the position of the carbon bearing the double bond, the carbon that bears the double bond is this sp2 hybridized. Okay, so keeping in mind that they have double bonds, single or multiple, okay? Single or multiple. Okay, and this number of double bond is the basis for their classification. So let's go again. Alkenes are what? Group of unsaturated hydrocarbons having the general formula CnH2n and hybridization of sp2 with double bonds containing one sigma and one pi. One pi bond and one sigma bond. Okay, so those are the 2 bonds. They are 1 sigma bond and 1 pi bond. Okay, so this is the general property that we use in describing alkenes. Now I said their common name is olefins, right? Remember, the alkanes are commonly called paraffins. These ones are called olefins, and it's from the word oleum. Okay, oleum. That is where the word ole is gotten from, and it means oil, right? Oil. So they are called olefins because they are oil formers. So this word actually means oil former. Means oil former. All right. So now, what are the so since we said they are unsaturated because they have double bond. Okay, that's made of unsaturation. They have double bond in their carbon to carbon chain, and since this is their general formula, we can create a series, a series called homologous series for them. And the first member, the reason why I'm going to engage in this one is because I didn't do the homologous series for alkanes. I'll be doing this because some people may not know that the fourth member of the alkene is not a methane, is an ethene. Keep in mind. So it means that there is no alkene that has a single carbon. The lowest number of carbon that alkene can have, which is the first member, is going to be what? 2 carbons. And since it is 2 carbons, the name what? Ethene. It still follows with the prefixes that we used in the order in alkanes. So when it is 1 carbon, remember we used meth. And I said here that we cannot have single carbon for alkene. Why? The reason is because there has to be a double bond, right, before we can say it is unsaturated. So if they are unsaturated and there has to be double bond, double bond has to be between a carbon and another carbon. Yeah, keep that in mind also, because if the double bond that you see in a chain is not between carbon and carbon, that hydrocarbon or that organic compound is not necessarily unsaturated. In fact, it could be saturated. Okay? For example, alkanone. Okay, let's not get into it. We are going to still do it in further videos so that you understand what I'm saying. But my point is that you call the hydrocarbon unsaturated if a double bond or a triple bond occurs between carbon and carbon. Does that make sense? So in this case, since the double bond must occur between 2 carbons, at least 2 carbons, then we cannot have methane. So meth is annulled for our case. Now if we have 3 carbons, then that's going to be what? Propene. Okay. Now the general formula is CnH2n. So it means that the formula of this guy is going to be what? C2, because in this case we have 2 carbons. Then H, which will be 2 times 2. That becomes C2H4. Okay. And structurally, this is drawn as C double bond C, then H, 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 H. Now notice that these guys, the molecules attached to the carbons bearing the double bond are attached at a particular angle. Yes. I did mention that they are sp2 hybridized. These carbons here are sp2 hybridized, and they have a bond angle of 120 degrees, okay, and maintain the shape, the trigonal planar shape. Okay, now here is it. I was thinking of something recently about releasing a video on Lewis structure, bond angle hybridization, all of those things, the link between them. So if you want me to do that, mention it in the comment section. I'm going to release it. I'm going to deal with many questions so that you are grounded in that, on that aspect. So they maintain a trigonal planar shape, so that's why you always see us draw it that way, okay, across the carbon bearing the double bond. Okay, so this guy is going to what? C, because 3, N is now 3, so that is C3, H what? 6. What you simply do is double this number, okay? Cn, H double N. Does that make sense? Okay, if it's 4 carbons, okay, so the shape of this one is going to be what? Like this. C, C, double bond, C. I decided to put the double bond here. Now it's going to be a single double bond, okay? 1 double bond, that's what I mean now, 1 double bond. Okay, so here we'll have this, H and H. Notice that for these ones, I attach them at 90 degrees. I've told you for convenience's sake. So this one will maintain an alkene type of geometry, right? Okay, so it means that this guy, this carbon here, is going to be what? Is going to be sp3 hybridized, while this one will be sp2 hybridized, sp2 hybridized. Does that make sense? Okay, I'm going to deal with hybridization even as I go to the next one. I'm going to deal with is the types, classification. Okay, I didn't mention that. We'll talk about the classification. Okay, now, so let me do one more step. We have 4 carbons. It's going to what? Boot, right? But this time boot in, yeah, boot in, and then we have our guy. 4 carbons is going to be C4, then double that's H8. Does that make sense? So what do we have? We have 1, 2, 3, 4 carbons. I could start with my double bond here. All right. Notice that I am putting it at the carbon that is at terminal carbons. Okay, in between terminal carbon and the next carbon or the preceding carbon. So, for example, this is a terminal carbon, this is a terminal carbon. If I put my double bond here, or I put my double bond here, it is the same, because if I flip the molecule, I'm going to have the same thing. So the same way, if I put my molecule here, or put my double bond here, or put my double bond here, the name will still be the same. So this is still propene. This guy also is going to have all of this attached around it like this. This is also going to what? Butene, okay? Butene, because the double bond is here. Now, if the position of the double bond be shifted, then this guy, the name changes to but2ene. Why? Because the double bond is now between carbon 2 and carbon 3. Does that make sense? Depending on which angle you are reading from, you are counting from, okay? Now, no, of course, it's still the same. Whether you are reading from here or here, it's still but2ene. Does that make sense? Now, my point is this, that the hybridization of all these carbons are not the same. This guy maintains a tetrahedral geometry. This guy also, okay? But this guy here maintains a trigonal planar geometry. Okay, so that means that this carbon here is sp3 hybridized, this guy is sp3 hybridized, this guy is sp2 hybridized, this guy sp2 hybridized. Okay, all right. So that's what we have for. If you don't understand what I mean by sp2, sp3, the video to hybridization is in the description below. So do well to see that video. Okay, so you will understand what I mean here. Alright, now let's quickly talk about classification. You will now see when an alkene can even have sp hybridization. Alright, so let's talk about the classification. Now, classifications. Now, based on the classification is based on the number of double bonds. This classification is based on what? The number of double bonds. So if a hydrocarbon has one double bond, if it has one double bond, it will be called a monene. Monene, that is monoene. Does that make sense? All right. If it has two double bonds, then our alkene is going to be called a diene. Okay? Now this diene is further divided into other types. I'm going to tell you how, because of the arrangement of the double bond in them. Now, for a like greater than diene, okay, we begin to have other divisions. All right. Now you see this guy, for three double bonds, what I have is a triene, okay, and greater than four and above double bonds, you have a polyene. Does that make sense now? All right. Now let's talk about the dienes. Now, the dienes can be divided into two again. No, three actually. They can be divided further into three types of alkene, diene alkenes. Okay, we also call them alkadiene. Okay, that's another name. Now, alkadienes are divided into three, namely conjugated, and that's what I want to talk about first. The conjugated, then we also have the isolated and the cumulated. Okay, no, let me talk about the isolated first. Now, isolated diene is when you have carbon to carbon chains like this now. And there's a double bond here, for example. Now this is just a skeleton I'm drawing, okay? So let me use it this way. So you have double bond here, and you now have the double bond far away from where you had the first double bond. The second double bond is at a position that is far away from the former double bond that you have. At least 2 carbons away. Once it is 2 carbons away, once the second double bond, an isolated is formed when when the two double bonds, are at least two carbons away from each other. Does that make sense? So you form an isolated hydrocarbon when the two carbons that possess the double bonds are at least two carbons away from each other. Then you now form a conjugated hydrocarbon when the two double bonds are one carbon away from each other. So because they are just a carbon away from each other, they form a conjugated system. I'm going to explain what conjugated, the effect of that conjugated system. Okay, so this is what I mean. Let's say I have my carbon skeleton like this, all right, and I put my double bond in the first one. Now, so if I skip one bond and now put my double bond away again here, then this is conjugated. Okay, this is what? Conjugated. Why is it conjugated? Now, it is conjugated because I have a double bond here and a single bond and a double bond. Now, it could also occur with trienes or polyenes. Okay, so I could have a double bond, a single bond, a double bond, a single bond, a double bond, like that. Once it is alternating double and single bonds between every single carbon, then it is what? A conjugated system. I'm using a diene now, for example, okay? So it's a conjugated system when you have what? Two double bonds that are just one carbon away from each other, such that there is alternating what? When there is what? Alternating single and double bond in the system. Conjugated is also what? When there is what? Alternating single and double bond. Okay, when there's alternating single and double bond, that's also what? A conjugated system. I'm going to talk about the effect of this conjugacy. Okay, so just conjugation. So just wait. Now, then the cumulated system is when there is no space, when a single carbon, a carbon atom, possesses two double bonds around it. Now, what does that mean? If I have something like this, look at my carbon skeleton now. I have this. Say I put my first double bond here, and then immediately I put my second double bond. Okay? I put my first double bond here, and the next time I put my second double bond. Then this is what's cumulated. There's something that came to my mind now. See, here I said two double bonds are one carbon away from each other. What that means is that, see, it's supposed to be two carbons away from each other. Okay? Do you know why I said so? So that it will not confuse students. The way I'm looking at it might be different from the way you are looking at it. Now, actually, the way it is, the way I'm supposed to put it, the one will be two double bonds that are one single bond away from each other. Okay? So it's actually two carbons. This is a double bond, then you have two carbons. Okay? Then this one will now be two double bonds that are at least three carbons away from each other. Please let's correct that. Let's correct that. Okay, because the way I want you to see it is, look, so there is double bond there, and then you have 1, 2, 3 carbons. Okay, 1, 2, 3 carbons. All right. So that's what I mean by that. So when a carbon atom possesses two double bonds around it. One carbon possesses two double bonds around it, then that's cumulated. That's cumulated. All right. Now the other thing I said here before was the way I was saying it was in terms of the single bonds. Okay. So if you had said that when two double bonds are two single bonds away from each other, then that is also correct. Okay. But I hope you understand. This is isolated because the double bonds are far away from each other. It's not immediately followed. For example, single bond and double bond and single bond, then double bond, no, that's conjugated. But if you have double bond, that's cumulated. But if you have double bond, single bond, single bond, single bond, single bond, double bond, single bond, double bond, then that is what? Isolated. Does that make sense? Now, in nature, you see these guys are very rare. Okay, cumulated alkenes are very rare. Albeit there is a question that is commonly asked from here. Now the hybridization of this carbon is sp2. The hybridization of this carbon is what? sp3. The hybridization of this carbon is what? sp2. But the hybridization of this carbon is sp. The hybridization of this carbon atom is what? sp. And why is it sp hybridized? It is sp hybridized because now you see it has a sigma here, a sigma here. Just like this one has a sigma here and a sigma here, right? But you now see this one here is a pi here, pi bond here for this one, pi bond here for this one. Now there's another pi bond here for this one and pi bond here for this one. And remember, only an sp hybridized carbon can have what? 2 pi bonds. Remember, if I have C triple bond C, okay, so this is going to be a pi, this is going to be a pi, and this is going to be a sigma. Okay, I once told one of my students who I told that this was sp hybridized. She said she didn't agree, and then I look for a way to explain. How do you explain a carbon that has 2 pi bonds around it? How do you explain that? There is a pi bond here and there is another pi bond here. So it is just what? An sp hybridized carbon, because that is what we have for what? For triple bonds. This carbon, at least you know that this carbon and this carbon are what? sp hybridized, okay? So since they are sp hybridized, it means that the molecule is linear. Here too, there's also a linear molecule. If you look at it, there's also what? A linear molecule. There's no branching on this guy, no branching. Just like we have on this guy. There's no branching. So this first pi bond was formed by what? The 2p sub y orbital, and this second pi on this guy will be formed by what? The 2p sub z orbital. Does that make sense now? Okay, if you don't understand what I just mentioned, just go to the video on hybridization, okay? But it's quite understandable here. So this guy is what? sp hybridized. Once you have a cumulated alkene, then the central carbon is going to be what? sp hybridized. And you know there is a name we call them, okay? When, in this case, if we are talking about this major carbon, this carbon will be called the alpha carbon. Then the next carbon beside is going to be what? The beta carbon. Here we have 2 beta carbons, this beta carbon and this beta carbon, okay? Depending on where we are reading from. This is alpha carbon, beta carbon, beta carbon. Do you understand now? All right. Now there are terminologies that we use for them, for their names. Okay. Now for carbons that are adjacent carbons, we use vicinal for them. Vicinal. And when a molecule is on the same carbon, when a molecule is on adjacent carbon, we call them vicinal. When a molecule is on the same carbon, we call it geminal. Okay. Now, for the vicinal, also we have 2 forms of vicinal. No, don't worry. I'm going to treat this, but let me just explain now since I've started. Now, there are 2 forms of vicinal. We have the anti and the syn form. Syn form means the molecule are on the same side. Anti-form means they are on the opposite side of each other. Or we say they are anti-periplanar. Don't worry, I'm going to mention and talk about all of this. But we now understand the types of what? Alkenes. Now, you see the conjugated alkenes are the most stable alkene. Okay, they are more stable than the isolated alkene, and they are and than the cumulated alkene. The conjugated alkene are more stable than the isolated alkene, and they are more stable than the cumulated alkene. Okay, now why are they more stable than both of this? Here is the reason. The reason is that, you see, because of this conjugation here, conjugated system here, there is resonance. The stability is brought about by resonance effect. Okay. Now, if not for my rush in trying to quickly cover these ones, I would have discussed all those effects for you before now. The inductive, electromeric, mesomeric, and resonance. But I will treat them after I've treated alkene, and alkyne, okay? But I'm still going to explain a little bit about what is happening here. Now, here's what happens. See, I did in this molecule continue like this, okay? Continue like this. Okay, now here's what will happen. Let me clean this. So we already know this, right? Now, why is this conjugated system more stable than isolated and cumulated? So that's what I want to show you now. So here's my conjugated system now. Now, here's what happens. I'm using the skeleton alone, please, so you should understand. Now, here's what happens. Now, one thing that happens is this, that helps this guy to be more stable, is that this pi bond, let's say this, you know, there are two bonds here, right? One sigma, one pi, one sigma, one pi. All right, let's go. So now here's what happens. This pi bond is easily delocalized. This pi bond is easily delocalized. Okay? See, notice. See, you see, alkenes are generally more reactive. Just listen to me first. Alkenes are what? Generally more reactive than alkanes. Or would I say they are corresponding alkanes? Generally, they are more reactive than alkanes. Why? Because of, and the reason is, this pi bond is a weak bond, okay, and that's their reactionary center. Whenever a reaction wants to occur with alkenes, which is generally or mostly addition reaction that we are going to cover under chemical properties, that reaction is generally addition reaction. So, and this center, this double bond, which is majorly the pi bond, is what their target center, this target center of the reagent. Why? Because the pi bonds are what? Are weak bonds. Therefore, I'm going to explain that when I begin to explain the geometry now. Their geometry is, they are formed by unhybridized p orbital that now come together in lateral overlap. Okay, so there's no way I will not say explain hybridization. So just calm down. All right. Now, alkenes are generally more reactive, and these pi bonds are what? They are reactionary center. But you now see with the conjugated system, in a non-conjugated system, that pi bond, those pi electrons are they are easy to break. They are weak bonds. Okay, they are weak bonds. So because of that, any organogen that is reacting, any organogen that is approaching, we approach at those pi electrons. But you now see this guy here. Think of them this way. After this is not the chemical explanation for it, but think of them this way. You know, I said that these pi bonds, because of this conjugated system, they are oscillating between here and here. What that means is that by resonance, what that means is that this pi bond will come here, this pi bond will come here, and then you have C double bond C, then double bond C and C. Okay, so what does that mean? It means that at a particular instance in time, this double bond came here, and then you have this, and this double bond came here, and then you have this. Okay, so also this thing is also going back. So what that means is that it's going back and forth, going back and forth at an incredible rate. Think of it that way. Okay, so when something is going back and forth that way, when an organogen wants to attack, doesn't know where to attack from. Think of it that way. Okay, that's the best way to understand it. Okay, that's the best way to understand it. So because of that resonance stabilization effect, an organogen cannot easily attack a conjugated system. Do you understand now? So what adds to the stability of this guy is what? The resonance stabilization that occurs here. Okay? Resonance simply means the continuous delocalization of the what? Of the pi electrons across two adjacent carbons. Okay? So these two carbons here are going to be oscillating, they are going to be shifting the position of the double bonds between each other. Do you understand now? So that is why these guys are what? More stable than cumulated or isolated alkenes. Now, let's talk about their geometry. Let's talk about their geometry quickly. Now, you already know that they are, for example, I'm going to use the simple alkene, like ethene, for example. Okay? And now, this is something that normally confuses students too. Now, we are used to writing alkene this way, drawing alkene this way structurally. Then a student will ask me, what about this guy? Yes, it is the same way. Now, the reason why I put this on the straight line is because of convenience sake. The way this is structurally is like this. Then there is, C double bond C first. That's what you should draw first, okay? C double bond C. Then there's going to be, you know, this one will have an H. So the H will come here. Then it has a CH3 because it's CH3, right? So there's going to be a CH3 here. Then here we have CH2. Does that make sense, right? Now, so this is what? Propene that I would have normally drawn on a straight line. This is the way it is geometrically, like if you want to show the actual angle, okay? Notice that the actual angle is going to be 120 degrees like I mentioned, right? Okay, so that's just for the case. So all those places where I put a double bond, there's going to be a kink in the chain. A kink means a bend, okay? There's going to be a bend in the chain. So that's why it is these guys that lead to the kinks that we observe in when you do fatty acids and alcohol. By the way, I'm going to begin a biochemistry series soon, okay? So make sure that you see everything, or you don't miss out on any of the videos. Okay, so see, what was I saying? I said that this is their geometry, okay? Every bond here is at 180 degrees from each other, okay? And it is planar, okay? It is just like on the plane of this board as it is, all right? Flat out like this, all right? Now, here's my point. Now, as it is like this, so you already know that we have the sigma, one sigma and one pi here, right? Now, because of, now, how is the sigma bond formed? Now, you know that the sigma bond is going to be formed by the sigma bond is going to look like this. So it's going to form with the sigma of this other guy, of the other carbon, okay? So this one carbon here, this one carbon here. So they form in the center. Don't mind my drawing. I've showed you that before in the other distance. So this one carbon here and this one carbon here. So they form their bond. Now, the unhybridized p orbitals, you know that the bonds that form, let me quickly talk about hybridization so that you will understand what I'm talking about. So this 2s, you know carbon in the ground state has 1s2, 2s2, 2p2, okay? Now here's what happens. There's going to be a promotion of, so these 2s, I'm not showing 1s because it's not involved in hybridization. Now, there's going to be, so the 2s initially will have orbital diagram like this, but there's going to be a promotion of one electron from here. This guy that has opposite spin here is going to be promoted. Initially what we had was this. So this guy is going to be promoted to the third guy here. And this is p sub x, p sub y, and p sub z, right? So what will happen is that after that promotion on excitation, only two of these bonds will now be hybridized, so that you now have a bond, an orbital that looks like this. 2s, 2p sub x, and 2p sub y. You know this 2p orbital. Now, I drew them on the same level, even though one is slightly shifted a little from this because it's higher energy than this. All right, 2p sub y. Now, this guy, 2p sub z as it is going to have one electron. So these two are hybridized. Okay, now the way they are hybridized is each of these guys will have a shape that looks like this. And keep in mind, I said it's going to be, the lobe of this one is going to be bigger than the lobe we had for sp3. That's the way it is, yes, with this guy. The lobe is going to be bigger, all right? So these lobes is what they used to form the sigma bond you are seeing here. This is sigma bond. Now you now see this unhybridized PZ of this first carbon. This one is for this carbon now. It's going to now form bond with the unhybridized carbon of this second carbon, all right? So, and how does that occur? That's going to occur by, you know that the P is also like a perfect dumbbell, right? Who is that? Yes, sir. It's a perfect dumbbell. So you're going to have a shape that looks like this. So they are going to form an interaction that you're going to see at the top and base of this sigma bond. So because of that, it does not allow for free rotation. Now, if the rotation be forced, for example, that is, if they eventually rotate, this pi bond is going to be broken. So think of it like a bond, like a band, okay? So if you have a band like that, the moment you twist it too much, what will happen? It breaks. So the same way, this lateral overlap that occurred, and when I mean lateral overlap, think of it, look at my hand, for example. Now this guy and this guy are together this way, so they are going to come together like this to interact with their electrons, okay? So, and that's why we say they are very, very weak bonds, okay? They are not formed by adjacent overlap, okay? You know that this one is adjacent overlap, where two of them are holding on to the electron and they are clinging together. But in this case, they are just interacting with their electrons, overlapping above and below the sigma bonds that is formed here. So, in a case where there is torsional strain that results in a twisting of the bond or a rotation of the bond, that pi bond breaks, okay? So that is why we have what is called a geometric isomerism with alkenes. And what do you mean by geometric isomerism? Okay, now there are two types of geometric isomerism. We have the cis and the trans isomerism. Now the cis is a German word for same, okay, and the trans is a German word for opposite. All right. Now cis isomerism occurs when you have two groups on the same side of. Now you see this isomerism. First note that it is considered across the double bond. Now, because students are usually confused about something like this. For example, look at this molecule. Now, this my molecule is 1,2-dichloroethane. Now, looking at this guy, because the two chlorine guys are attached on the same side of the carbon chain across the double bond, then it is a cis. So I'll start with cis if I want to name it. Cis 1,2-dichloroethane, okay? But if I changed this orientation such that I have this in the opposite direction, then I have a different molecule entirely, okay? So this molecule is now trans 1,2-dichloroethane. Now you might begin to think that how are they different? Now they're actually different because by physical reaction, this guy actually has is at a lower potential energy than when the chlorine was on top. The cis isomerism makes the heavy groups, these two heavy groups, they will be interacting at that above that plane. So because they are interacting above that plane, there is steric, there's a kind of steric disturbance. Okay, so because of that, the potential energy is higher. But if this one was brought here so that we have the trans system, the trans isomerism, then that guy is going to have a lower potential energy. All right, so that's why they are very different. Now, here's what now confuses students. Listen, this is what confuses students. Now, if I now put this chlorine here and put this chlorine here, for example, and I put H here, then they now say, is this trans or cis? Now, listen, this is not trans or cis. Okay, why? Because the molecule is not distributed across the double bond. The molecule isn't what? Distributed across the double bond. So for example, this guy is going to be named simply as 1,1-dichloroethene. Okay, 1,1-dichloroethene. No cis, no trans. Why? Because there is no distribution across the double bond. It's when molecules are across the double bond that you have a cis and a trans system. Now, for example, look at what I gave you the other time. This is just to test your understanding now. Now look at this, and a system where I have this my double bond still. Now which one is going to have a lower potential energy? You're correct, this one, of course. Why? Because it is what in the trans isomerism. Then this one is going to have a higher potential energy. Why? Because it's cis. Now, these guys can be cis and trans system. Why? Because, and you know when you're naming them, it's going to be what? Cis cis 1-chloropropene, right? Cis 1-chloropropene, and this one will be trans 1-chloropropene, sorry, trans 1-chloropropene, and this one will be cis 1-chloropropene. Now here's my point. Now that doesn't change, the only difference is the name, that trans and the cis that you have there, okay? So that's about their geometry. We have the cis and trans isomerism. Now don't confuse it with, as I was student who was asking about the difference between this isomerism and stereoisomerism. Geometric isomerism is different entirely from stereoisomerism. Okay, in stereoisomerism, where we now begin to talk about chiral centers, okay, non-superimposable mirror image, optical isomerism, that is now, okay, all right. So, all right, so that is that about their shape. Now, the next thing we talked about their classification and their structure. Okay, now let's talk about their mode of preparation. So here is where you should really pay close attention. You have to pay close attention now. Okay, let me list the methods that we're going to talk about here. Now, under mode of preparation, methods of preparation. Now, the first method that we're going to look at is the, I'm going to talk about the ones that have to do with mechanism first, okay? So, no, they all have their mechanisms, but the one I want to, the mechanisms I probably would explain is the dehydrohalogenation. Okay, dehydrohalogenation of alkane. Then the second is dehydration again, dehydration of alcohol or alkanol. Then the third is reduction of alkyne. Reduction of alkyne. Now another method of preparation is dehalogenation. So what do you see? All you're seeing here is what? An elimination reaction. Elimination reaction. In most of the cases, elimination reaction. Reduction, no. Is it reduction of alkyne? For reduction, it will be of alkane, yeah? Of alkane. What's reduction? Addition of hydrogen. Okay, yeah, so it will be of alkyne. Then if it's alkane, then it will be what? Removal of hydrogen. So that will be dehydrogenation, okay? But I probably might not cover that. Let me just add it. Dehydrogenation. Okay. The other one I would like to cover is the Wittig reaction. Now, you might already know how what the Wittig reaction is, but probably you may not know the what's it called now? The mechanism. So I'll cover the mechanism here. Then Now, I may not cover this one, I will just explain it. Retrodiol or alder reaction. Okay, there is a diol-alder reaction, which is one of the processes by which we prepare a conjugated and a ring system. Okay, but the retro, which is the reverse, does that make sense, of that reaction? So we're going to talk about the dehydrogenation first of alkane. Dehydrogenation, dehydrohalogenation. Now listen now. The general reaction is where we have a particular RAC that is bonded with a halogen and another C that has H, okay, insufficiency, all right? So what we want to do is we want to remove one hydrogen and a halogen. Does that make sense? The hydrogen will be removed and the halogen will be removed. So we are saying that we subtract what? HCl, HBr, HX. Okay? Then at the end of the day, we are going to come up with RC double bond CH, CH2. Now, how does this reaction proceed? That's what we want to explain now. First, note that it takes place in the presence of an alcoholic. It takes place in the presence of an alcoholic alcohol and base. Okay, a base that is in an alcohol. All right. So, for example, KOH, which is a strong base. Okay. So, a strong base and an alcohol. That is where this reaction proceeds. Now, what happens in that reaction? What happens? Here's what happens. Now, I'm going to talk about what we call the saytzeff's rule. But before we do that, let's talk about the mechanism of the reaction first. So, let's say, for example, I had this guy. I wanted to okay. Now, if you have this, now what will happen? Now, you see this guy can be broken down into K and OH, right? When it ionizes, K plus and OH. Now, what happens? This base is going to come and abstract this guy. All right? Now, by the time this guy abstracts, by the time this base is abstracted, by the time this hydrogen is abstracted, now here's what happens. There's no, we'll not talk about the saytzeff rule directly. Okay. Now here's it. Now, you see, when this guy abstracts this guy, and this guy joins the solution, usually the dehydrohalogenation there are two types of depending on where you want to abstract you want to remove your HX from, we have two types or three types. We have the tertiary, the primary, and the tertiary, the secondary, and the primary. Okay, in that sequence. Okay. Now listen. So this one I'm using here is I want to abstract my Br and my H. Okay. So at the end of the day, I'm going to be forming a compound between. I'm going to form an alkene, a double bond that will be between a secondary carbon and a primary carbon. Okay, so in this case of dehydrogenation, what will happen is an E1, E2 mechanism. Now, what does E2 mechanism mean? What does an E2 mechanism mean? It means elimination by molecular reaction. Okay? Now, why is it bimolecular? That's the name of E2. E means elimination, 2 means bimolecular. Now, why is it bimolecular? The reason is because the rate of the reaction is dependent on the rate of two substrates. So, substrate 1 and substrate 2. Now, what are the two substrates in this case? So, as this base is attacking the hydrogen, immediately also this bond, which by inductive effect is already polar, okay, will now what? The bond will break and the electrons will be abstracted by this guy. So there is cleavage of this bond. At the same time, there is what? So this bond will move here, and this bond is what? Being taken, as this bond is being taken by this bromine. Okay? So, alright, so I said that it is an elimination reaction. It is bimolecular. Why is it bimolecular? Because the rate of the reaction depends on what? Two substrates. What are two substrates? This base that is attacking the hydrogen and the leaving group. Okay, so this leaving group is leaving because now it has to be a good leaving group. So for example, the degree of leaving group also with halogens is somewhat like this. Iodine is a better leaving group than bromine, which is also in turn a better leaving group than chlorine, and which is a better leaving group than fluorine. Okay. I think this is correct, yes. All right, so what that means is that this guy is going to live in this order, all right? Okay, now here's my other point. Here's the other thing. This has to be a good living group. Then, so there are two substrates there, this one and the base that is being what? Attacked. So that simultaneously, as it is abstracting this guy, then we have as this guy is abstracting this guy, then we have the living group also what? Living at the same time, leading to the formation of what? A double bond between both of them. Now, the double bond that is going to be formed between this guy and this guy. CH3, we now have C double bond CH2. Okay? Now, so put CH here. CH2. Now, you may not begin to think that why did we not abstract the hydrogen from here? So either ways, whether the hydrogen here is abstracted or the hydrogen here is abstracted, we are going to arrive at the same answer. But in a case where there are two possible products that can be formed, then what is called the saytzeff's rule comes to play. Saytzeff is a scientist that propounded how this reaction takes place. I've explained the E2 mechanism now, right? I said it is bimolecular because depending on the rate of reaction, depending on what? The substrate. And no carbocation is formed. Keep in mind, no carbocation is formed. Why? Because even though secondary carbocation can be formed here, it will not be formed because E2 mechanism. What will happen is to just what? Proceed in this direction. Okay? So what that tells you is that this kind of reaction can actually still proceed with what? Can actually proceed with what? An E1 mechanism. So let me tell you how that proceeds. But before we talk about that, let's talk about the saytzeff's rule. The saytzeff's rule. There are two ways it can be spelled. Is that we spell this way? Saytzeff's rule or saytzeff's rule. Okay? The problem is that the day we gave birth to him, we didn't know how to spell the name we received. So there are two spells. Anyhow you spell it, you are correct. All right. Well, I don't know what the problem is. Maybe it's the convention, maybe like American and British, I don't know. but the two spellings are accepted anyway. So saytzeff propounded that when there are two possible products, for example, as we have in a case like this, for example, now this is 2-bromo butane, right? Butane, right? 2-bromo butane. Now look at this. How does this guy undergo an elimination reaction? Now this guy is also going to undergo an E2 mechanism. So the mechanism of this reaction is going to be an E2 mechanism and or E2 elimination reaction. And what that means is that when the base approaches, okay, the base can do either of two things. Let me spread this out, okay. Now, the base can do either of two things. Either abstract this hydrogen here. Now, notice, the base will not abstract this hydrogen. No, let me first talk about saytzeff, then I'll talk about which hydrogen is abstracted, which hydrogen is removed. Once the base removes this hydrogen, this bond is going to come here, and this bond here is going to cleave in this direction. So, is either it approaches this hydrogen, or this guy approaches this other adjacent hydrogen. Keep in mind, it will always attack only the adjacent or vicinal hydrogen. It always attacks what? The base always approaches what? The vicinal hydrogen. Vicinal hydrogen. Now, it does not take the germinal hydrogen. Germinal hydrogen, thank God I already explained that thing. Germinal hydrogen is the hydrogen that is on the same carbon as the guy that is being removed, as the guy from which the halogen is leaving, okay? So, this guy can either abstract this hydrogen or abstract this hydrogen. So, here there are two possibilities. So, in the first possibility, here's your product. What you will form when this guy is abstracted, for example, is CH2, double bond C, H, then CH2, CH3. So this is the first possible product, plus the second, so this is a mixture of product, of course, that's what I'm talking about. Or I have CH3, CH, C, double bond CH, and CH3. So this is what but 2 in here, but 2 in, yes, and this will be 1 butene or but 1 in or butene. Okay, so this is butene, right, and this is butene. So where the possibility of forming a butene is or a butene is, the major product according to saytzeff rule is going to be the most substituted, and the minor product will be the least substituted. All right, so looking at this carbon here now, this carbon here is less substituted than this carbon. This carbon here has 2 hydrogens, and I'm going to explain in 2-3 different ways so that you understand. So the first way is that the hydrogen that will be abstracted will be the hydrogen of the most substituted carbon. And where is the most substituted carbon? There's an alpha carbon, these 2 beta carbons. I already explained that, right? So these 2 beta carbons are the possibilities from which we want to abstract our hydrogen, right? So this is the most substituted. This beta at this point here is the most substituted carbon. So it's the one from which you can abstract hydrogen, right? So the hydrogen is going to leave from this guy, and this one is the least substituted. Why is it least substituted? This one is least substituted because there are 3 hydrogens, 1 carbon, but here more substituted than this guy because there are what? 2 hydrogens, 2 carbons. So this guy is substituted by if this word HHH throughout, it will be an ethane and a methyl, and then 2 hydrogens. But this one has a propane, ethane and methane for this guy. For this one, But for this one, we have only a propane. The rest are hydrogens. So it is least substituted. So we call this beta carbon a primary carbon. So the second way to explain is that a primary carbon is unlikely to be the one, a primary carbon, okay, is unlikely to be the one that will be formed, that the double bond will be formed on, or that the hydrogen will be abstracted from. Is more unlikely than a secondary carbon, and a secondary carbon is more unlikely than a tertiary carbon. Another way to explain it is this: the hydrogen of the carbon that is attached to more carbon is the one that will be removed. I'm going to explain that again. The hydrogen that belongs to the carbon that is attached to more carbon is the one that will be removed. So for example, this hydrogen is removed, and not this one. I'm going to explain why it is not this one. The hydrogen here is going to be removed, be the one that will be removed. Why? Because this carbon is attached to two more carbons, according to saytzeff's rule. So then this hydrogen will be the unlikely product or the minor product because it is attached to less. This hydrogen is unlikely to be removed because the carbon that it is attached to only one carbon. I'm going to give one more example before now explaining why it is this hydrogen and not this hydrogen that is removed. Okay, now this hydrogen can also be removed, but in most cases it is this hydrogen that will be removed. Now listen, look at this case. For example, if I have something like this, all right, so look at this guy now. This guy is attacked by an alcoholic KO. Alcoholic KO. Looks like he's drunk, so he wants to attack this guy because he's drunk. All right, now listen. Now, how does this guy attack? There are two possibilities according to saytzeff, right? What is the first possibility? The minor product and the major product. So I'm going to clean this one out. I'm going to clean this one out so I can understand what I want to, the product I want to write there. Now, why is this guy, what are the two products rather? The first product is CH3, CH, because this one will be taken and this one will be taken. Yeah? This one will be taken, this one will be taken. So we have CH also. This one will be taken, this one will be taken rather. Okay? Then C, double bond rather. Then C, CH3. Okay? CH. CH3. So this is the first product, this is the first possibility. The second possibility is, and okay, one of them will be the minor, one of them will be the major product. So we have CH3. What I mean minor product and major product, it means that like 90 to 95% will be that major thing, then maybe 5% or less will be the other thing. Okay? So in the case where you are told to give the answer to a reaction, write only the major product. Write only the what? The major product. So we have this guy, CH2, CH, double bond C, CH3, 2. Okay? So in this case, it means that what? This guy is taking, for this one, you know that for this one is taking, this one leaves with the bond, right? And this one is abstracted, right? This one is abstracted, isn't it? Okay, sir. Is the hydrogen that is abstracted, the bond goes here. Does that make sense? Okay. Now listen. Why in the second case, this one is taken, now, this hydrogen will not be, the orientation will change, okay? Because I think it will not take it from there. So what will happen is that this one will switch position. It becomes CH3 here. Remember that there is 180 degrees rotation is permitted on single bond. So it will switch position, okay? So that this hydrogen will be taken. Does that make sense? So those are the two possibilities. Now, according to saytzeff, which one will be the major product, which one will be the minor product? A or B? Correct, B. This will be the what? The major product. Now tell me why. Tell me why. Tell me why before I say it. Tell me why. Yes? God bless you. Because this carbon is attached to three other carbons. 1, 2, 3. But with this carbon here, this is attached to only 1, 2 carbons, right? So because of that, this one is said to be the most substituted carbon, or the carbon with less hydrogen. So the carbon with less hydrogen is the one that hydrogen will be removed from. You know, the Bible said that the one will take from the one that has less. Whatever, yes, something like that. So my point is that this guy that has less hydrogen is the one that will lose the hydrogen, and what will happen? The bond will not be formed between both of them. So this will be the major product and this will be minor product. Do you understand now? This and this. Now by which mechanism will this guy take place? Now this one here can actually take place by E1 mechanism. I'm going to delve more on E1 mechanism when we get to dehydration of alcohol. Okay, but let me just explain what E1 is. You know, just like E2, we said E means what? Elimination. And what does the 1 mean? This one means what? Unimolecular. Now what does E2 mean? Elimination bimolecular 2. E1, elimination unimolecular. Why is it unimolecular? Because the rate of reaction depends on what? On only the product. Only one substrate, rather. The rate of reaction depends on only one what? One product, one substrate. And what is the one substrate there? Now what happens is this. Because what happens is this. This one, the moment this thing is approaching, the moment the organogen, the base in this case, okay, is approaching this place, this one can already leave. That is, this one can leave first, okay? You mostly understand this is dehydration. That's the most common example of E1. Now this one can leave. Once it leaves, what will happen? Then, you know, it leaves with the bond, right? So let's assume this one has left now. We have Br minus. What will happen here? There is what? An electron deficient center. And what's an electron deficient center? It is what? A plus. Alright? We call it a carbocation, okay? Or carbonium ion. Carbocation or what? Carbonium. Now, the reason why this carbonium can form is this. Now, the reason why the carbonium can form is this. There is, now there is something called a hydride shift that can also happen here. Because if the carbocation is formed on this one, it will not be as stable as if it were formed on this one. Okay, why? Because you are not substituted on this carbon. This carbon is attached to 1, 2 carbons. Why this carbon is attached to 1, 2, 3 carbons? So this one is going to form a more stable carbocation than what? If you have not seen video on Alkenes, see it so that you understand what I explained about carbocation, okay? So, by the way, I'll still drop another video on it. Carbocation and carbonium explained separately. So the carbocation that will be formed by will be stronger than this guy. So because of that, you know this one was attached to hydrogen before. What will happen is that there will be a hydride shift. Okay? So that this hydrogen, this thing can come here. I'm going to explain hydride shift with dehydration. But just understand that this carbocation can be formed easily here. So because of that, the case where carbocation formation can happen on this is where I have, let's say I have hydrogen here and I have bromine here. So once this one can leave easily. Once it leaves, then there is a stable carbon that is formed. So easily this one can approach this one and do what? And take it. Does that make sense? And once it takes it, then there's a bond formation of a double bond formation here, and then we have our major product. Does that make sense? Okay, so the name of our compound is going to be what? 2-methyl, 2-methyl, 1, 2, 3, 4, 5, pent 2-ene, okay? 1-methyl pent 2-ene, or 2-methyl pent 2-ene value. Alright, so that is that for saytzeff rule. Now, there is an anti-saytzeff rule. And what is an anti-saytzeff rule? It's called the Hofmann's product. It's called the Hofmann's product. That's how you have to stay. Just stay and listen. You are going to understand everything by the grace of God. Just keep listening. Now, we have the Hofmann's product. Now, what is the Hofmann's product in this case? What's the Hofmann's rule? We have the saytzeff rule and the Hofmann's rule. The Hofmann's rule now is the anti-saytzeff rule, and you remember that the saytzeff rule says that the most substituted alkene is the one that is likely to be formed, right? Hofmann's rule now says that no, in a particular condition, the most substituted alkene will not be formed, but the least substituted is the one that will be formed. It's just the the opposite of this one. Now, when does it happen? Now look at this guy. Look at this guy now. Now look at this guy. You know that according to saytzeff rule, the product that should be formed is 2-butene, right? 2-butene. But Hofmann said that if this guy were approached by a bulky base, so in the presence of a bulky base, what will happen? The least substituted alkene is formed. That's the Hofmann's rule. But saytzeff rule says that the most substituted alkane will be formed in the presence of normal base, okay, not a bulky base. The product will be what? The most substituted alkene. But Hofmann's product is saying that in the presence of a bulky base, the least substituted alkene will form. Now, what's an example of a bulky base? For example, we can have potassium, e.g., in the presence of a bulky base like tert butoxide, potassium tert butoxide. And that's going to be TBU, okay. This is the short form, okay. So this, in the presence of this, for example, what will happen is that we are going to form, the reason is this, because of steric hindrance. Steric hindrance makes this guy unable to approach the bulky group here too. So bulky group cannot approach bulky group. Do you understand now? So in a case like this will be the major product, but we now call it the what? The Hofmann's product. Okay, this will be the Hofmann's product. Then the other one, the second one we formed the other time will now be what? The minor product. So this will be the major product if this were to be what? Tert butoxide, for example. Do you understand now? So that is going to be, I used sodium here, I used potassium here. So it's the same, you know. Okay, so do you understand now? So this is going to be the Hofmann's product, and this is going to be the major product according to Hofmann, and the other one will be the minor product. If this was what? A bulky group, and I've explained why here, that a bulky group, tert butoxide, means there is CH3, and then there is 1, 2, 3 OH. So this has steric hindrance. So because of that steric hindrance, it cannot approach another bulky group, because there is bulky group in the most obtuse, right? And there is bulky group here in the base that is approaching. So because of that, it's not easy to approach. And then because of that, it will easily just take the hydrogen that is closest, that is easiest to take. Any available hydrogen. Does that make sense? All right. So that's that. All right. So that's that on dehydrogenation. Now let's go to dehydration. Please make sure you are subscribed to the channel. Please subscribe to the channel. God bless you. So that you will not miss out on all of these kind of videos. I'm going to start a biochemistry series, like I said, soon, very soon. Like as soon as maybe tomorrow, because some of my students have already started lodging some complaints about some things. So I need to. All right, so we have, what did I want to? The next one, dehydration. So since you already understand how the mechanism takes place, we might not stay long on this at all. Dehydration of alcohol or alkanol. Now, give me an alkanol. For example, I'm going to have, now majorly, depending on the kind of alcohol. So you know that we have primary alcohol, we have secondary alcohol, and we have tertiary alcohol. So an example of a primary alcohol is ethanol, for example. Why? Why is it primary? It is primary because, so let's just put CH3 here. It is primary because the carbon that bears the OH group is attached to only one more carbon. This carbon that bears the OH is attached to only one carbon. So this is called what? Primary. Just think of it as attached to one carbon. This one will be attached to what? Two carbons. This one, the carbon bearing the OH will be attached to what? Three carbons. So for this one, you're going to have what looks like CH3, then C, OH, H, and CH3. So this guy here is going to what? A secondary carbon. Why? Because this carbon that is bearing the OH is attached to what? Two other carbons. Does that make sense? Then for the tertiary, to be attached to what? Three other carbons. So you will have COH, then you have your CH3, and your CH3, and your CH3. So this is what? A tertiary carbon. Now, in this order, the degree of the possibility of engaging in an E1 reaction it decreases. Okay? So with E1 mechanism, with E1 mechanism, tertiary alcohols are more likely to engage in E1 than secondary, and these ones are more likely than what? Primary. Okay? And never, in fact, we say very, very greater, that's made of this, right? Very much greater than primary. Okay? So, and this one, and methyl is the impossible one. Okay? A methyl carbocation can pretty much not form. Okay? Now the reason is because E1, right, we said is elimination what? Unimolecular, right? The reason is this, is what? The reason is this, that the rate of reaction here, as I said, is depending on what? Just the one substrate, right? Now, the reason is this reaction rate is dependent on, it depends on the rate of formation of the carbocation. Okay? So the rate of formation of the carbocation is what this reaction depends upon. So if that is the case, then a stable carbocation has to be formed. So if a stable carbocation must be formed, then we must first form a good living group, right? So it takes place first in the presence of a in a protic solvent. If the solvent is not protic, this reaction cannot occur. Why? Because alcohol has to lose OH group. And how does it have to lose? How will it lose the OH group? It loses the OH group by protonation. See, this is just big grammar. Protic means a solvent that protic, that is proton, right? A solvent that contains hydrogen H plus, that can donate OH plus. Does that make sense? So if that's the case, then what will happen? That proton that is donated to OH rather will form what? Water. And once you form water, water is a good living group, right? Water can live. And once water lives, what happens? Then there is what? There is now deprotonation again. So protonation followed by what? Followed by what? Deprotonation. I will explain why. Remember I said in the initial video that when you have a carbocation formed, an adjacent carbon that has hydrogen, the hydrogen there will be acidic. Does that make sense? So because of that, it can be removed. Okay? Because the hydrogen, let me explain what I'm talking about here. So I have, let me use this guy, a secondary carbocation, a secondary alcohol. So I have this guy, for example, I'm going to explain a hydride sheet later using dehydration. So this guy takes place in the presence of an acid, H2SO4 for example, or H3PO4. Okay, if it's H2SO4, it will not be conc, it will be diluted H2SO4, but in the presence of under high temperature, okay, about 170 to 180 degrees Celsius. All right. Now listen. What will now happen? Here's what will happen. You know, because there is alcohol here, there is an acid here. What will happen? An acid is going to generate what? H plus. Now this H plus that is being donated by this guy is going to attack this guy. Does that make sense? So remember that this guy, the level structure is going to look somewhat like this here. Right? So what will happen? This H plus will attack this, and by attacking it, what will it do? It will leave with the bond. Why? Because it will form, this thing will become CH3C. Then we have OH that was there. Then it has now been added to what? So a proton has been added to it. So you now form H2O, right? Which is water, right? And you have your HCH3. So what will now happen? This guy can now leave. Does that make sense? This guy can leave. So once this guy leaves, what do we form? We form this. Okay? Now what is this? This is what? A secondary carbocation. Does that make sense now? Now this secondary carbocation is quite stable. What stabilizes it, I've told you before, is what? Hyperconjugation effect. But keep in mind that there will be higher hyperconjugation effect with what? A primary, a tertiary carbocation. There is higher hyperconjugation effect, so there is more stabilization effect. Alright. So after this has been formed, then what will now happen? This one, this hydrogen here will now be abstracted by another water that is inside this thing, because it has become acidic. Okay, the adjacent carbon will lead to this one being acidic. So because of that reason, what will happen? This one can be abstracted by water, and this bond will now do what? Cleave here. Do you understand now? The bond will now go there, and what happens? Then what will now happen? You now form hydrogen will now go. Then you have H3O. H3O4, H3O plus rather, inside the solution. And then what will now be formed? These will now be formed. Keeping in mind that saytzeff rule still holds. So it's possible that, it's likely that it is this hydrogen here, there are two possibilities rather. Either this hydrogen here is attracted or this hydrogen here is attracted. So the major product is what I want to draw now. You have CH3, CH, double bond CH, and CH3. So this is going to be the major product. Do you understand now? This is going to be what? The major product, or saytzeff's product. This is the saytzeff's product. Alright. So that is the case with what? With an E1 mechanism using dehydration. Alright, now something else sometimes occurs. We could have a hydride sheet. For example, let me change this to This is, let's add a methyl group here. So this becomes from butanol or butanol, it becomes 2-methyl butan, 1,2-methyl butanol. Okay? So the mechanism is a little bit different, just a little bit different. Keep in mind that the saytzeff product will still be formed. Okay? What will be the saytzeff product in this case? This, initially, we said that, yeah, it's quite the same, This one's still forming, but here's what happens. You know that if it were like this, this is when the hydride shifts can occur. Let's put this guy here, the OH here, and this will now be 2-methyl butanol. 2-methyl butanol. Now in this case, what will happen? This guy will leave, then a stable carbocation is formed. No, I want a case where let this guy be OH. No, it's still the same as what I wrote before. If this guy leaves, a carbocation is formed there, yes. Now I got what I was looking for. It's the same as what I wrote before. The OH was on top, it's the same. So H plus the approach still, right? And we'll come and protonate this guy. After protonation, what will happen? C will now have CH, CH3, CH, CH3, CH3, and our carbocation. Here's what now happens. What happens is that you know that this guy will be protonated, right? This guy here will be deprotonated, right? So before that deprotonation occurs, there's going to be a hydride shift. And what do you mean by hydride shift? This hydrogen here will shift here, and this carbocation will shift here. So what do we have? We'll have what looks like this. So what will now happen? Then our water can now deprotonate this guy, and this bond now clips. Do you understand now? So this guy will deprotonate this guy, then the bond will now fall here. Now, why did this hydride shift take place? A hydride shift normally takes place in order to stabilize, to form a more stable carbocation. In as much as hydride shift will only take place under two conditions, where the carbocation that is formed is not as stable as the carbocation that will be formed. And what is the carbocation that will be formed? The carbocation that will be formed provided that the adjacent carbon is more substituted than that alpha carbon. So let's call this our alpha carbon, this will be our beta carbon. So knowing here that our beta carbon is more substituted than our alpha carbon, what will happen? It will be a hydride shift. And what will happen? A hydride shift will occur, and then the formation of a more stable carbocation is achieved. Then what will now happen? Then you form your alkene here. All right. So that is that for dehydration of alcohol. Now let's go to the reduction of alkynes. Reduction of alkynes. And that makes sense. You can also call it partial reduction. What does partial reduction mean? It means that you know that our alkyne is triple bonded, right? All right, so when we reduce this, what will happen? It will undergo partial reduction. Now, it doesn't just occur, it occurs in the presence of Lindlar's catalyst. Okay? Now, what will happen? Once this guy occurs, once this reduction occurs, it always gives rise to a cis, that's cis. It gives a cis alkene. I'm going to, with this one, okay, for example, let's put R here and put R prime here so that you understand when I say the cis alkene that will be formed for this case is what? R, C, and R prime. Does that make sense now? So this is what you form, cis alkene. Now this is using Lindlar's catalyst, but using the procedure that goes with Beck's reduction. This is another scientist. Beck's reduction forms a trans alkene. It forms what? A trans alkene. And what is Beck's reduction? Good morning. Yes. Now, what is trans reduction? Now, when you have this triple bond here, what will happen? Once the reduction takes place, first, this one takes place in the presence of sodium that is immersed in liquid ammonia. Okay? So, once the reduction takes place, you are going to get a trans alkene. Does that make sense? So you see that this one takes place in presence of what? Lindlar's catalyst. This one takes place in presence of this guy. Now, the other thing is you should know is the Lindlar's catalyst itself. Now, Lindlar's catalyst is basically composed or comprised of poisoned palladium. Poisoned palladium. How do you spell palladium? PD, yeah? Okay, poisoned palladium. And what does poisoned palladium mean? Palladium that has been immersed in quinoline. Quinoline, that's why we say it's poisoned, okay? So it's a poison though. So it's immersed in quinoline, okay? And so poisoned palladium and in the presence of CaCO3, calcium carbonate. So poisoned palladium and CaCO3 makes up what? Lindlar's catalyst. And when that occurs, what you get is what? A cis alkene. And using Beck's reduction, you form what? A trans alkene. You form a trans alkene. So that's that on reduction of alkyne. Let's talk about the dehalogenation. I mean, I don't need to give an example of this again. Okay. Now, let's talk about dehalogenation. Okay, so dehalogenation now. Dehalogenation. So what will happen? We have an alkane, okay? So the mechanism will be quite similar, okay? Only that this one is removal of halogen, yeah? So we have something like this. Okay, I wanted to explain something about the fact that this hydrogen is the one that will be, you know, we have Br here. And I said that it is this hydrogen that will be removed, not this hydrogen. It's because the deprotonation also wants to see this orientation is called the antiperiplanar. I'm just mentioning that in case you see it, you come across it. This antiperiplanar is the conformation in which the deprotonation takes place. The reason is because of steric hindrance again. Okay, so in the case where we have CH3 and all of that, now what will happen is that this guy, the proton best takes or abstracts this hydrogen that is in the antiperiplanar position to this Br, to this leaving group, okay? That is for dehydrogenation that I explained the other time, or the dehydration, okay? I just remember that I didn't mention it again, all right? So because here also, this reaction also occurs with anti-conformation. This is also called anti-conformation or antiperiplanar conformation. Okay, even though this one is not planar, okay, because you know it is sp3. These carbons are sp3. So here's my point, that this guy will be abstracted, yeah? This guy will leave and this guy will leave. So what do you mean? Minus what? Br2. Okay? It occurs in the presence of CCl4 tetrachloromethane. And then what you get is what? CH and double bond CH2. So that's what you have there. With dehalogenation. All right? With dehalogenation. Now, let's talk about the Wittig reaction. Let's talk about the Wittig reaction. All right. Now you see the retro-diol-Elder reaction. Okay, now the diol-Elder reaction. There are two scientists, German scientists, that they discover that if you react a conjugated diene with a suitable another suitable alkene or diene lover, okay, we call them dienophiles. I will not mention the diene reaction in chemical distance, okay, because I'm not really good at the mechanism. But what happens is in that reaction is that the diol-Elder reaction, just for your further reading, a conjugated alkene is reacted. So for example, a conjugated alkene like 1,2-butene, 1,3-butene, okay, or 1,3-diene, 1,3-but. So but 1,3-diene, okay. That's a conjugated alkene, for example, will be reacted with a dienophile. A dienophile means a diene lover. Okay? So when a dienophile, the dienophile could be another diene, another alkene, or an alkanone, or an alkanone, whichever it is, as far as a dienophile, then what you give rise to is a ring system. Yes or no? So the reverse of the reaction is a retro-diol-Elder reaction. You produce an alkene, usually a conjugated alkene, depending on what gave rise to that retro-diol ring that is formed. To that diol-Elder ring that is formed. And this is diol. Okay. All right, so I wanted to talk about the Wittig reaction. All right. The Wittig reaction takes place in the presence of what is called, let me take water please. All right, so that's okay, so now let's talk about the Wittig reaction. The Wittig reaction takes place in the presence of what do they call that thing? The trimethyl methylphosphine, okay, trimethylphosphine, right? And an aldehyde, okay? So an aldehyde is reacting with what? Trimethyl, triphosphenylphosphine, sorry. I said trimethyl. Triphenylphosphine. So this is triphenylphosphine or phosphine. Okay? It was named after George Wittig, okay, in 19s, whatever, maybe 1930 something. So now George Wittig reacted triphenylphosphine with an aldehyde and was able to form an alkene. Okay? Now, in the process, he was able to produce what is called betaine as an intermediate product. Betaine. Alright? Alright? So an aldehyde will react to this, but so let me write the mechanism, the way the mechanism proceeds. So a triphenylphosphine will first react with an alkyl halide, okay? So let me use my alkyl halide to be something like this. My alkyl halide, alright? So like it could even be like R prime CH and R, right? So CH2, right? CH2, this is alkyl halide, yeah? Right. So when they react, they are going to form what's this salt, alkyl halide. This was the H, X, right? But it has to be two alkyl, right? It has to be a large alkyl halide, a large molecule. Okay, so that's why I'm putting two R's. Okay, so you have this. Excuse me. Okay. So you will have this. You have the CH2, RX, and alpine. So what will happen is that they're going to produce this salt that will still be bonded with RCH2, R, and X, right? Alright, so usually we put this outside. Okay, then you now react this guy with a base, a strong base. Now once you react it with a base, what does a base do? A base deprotonates, right? So the moment you deprotonate this guy, you are going to form this. Then this one will also live with the base, okay? Other products are formed that this one will live with, and then you have what looks like this. Then this is what will now react with our aldehyde. Okay? Once it reacts with our aldehyde, what will happen? It's going to form betaine. Then betaine is going to look like this. this will now form bond with this carbon. Then what happens is that, you know, there is already a double bond here. Okay, I didn't put that, sorry. There's already a double bond here. This double bond will attack this double bond, and then this bond will cleave to this oxygen. So you now have a minus here. Does that make sense? So when that occurs, then you have this C, then that is already bonded with this. Then this guy is bonded to R, all right? Okay, so what will happen is that there's going to be a bond formed here, okay, because this guy is going to attack this guy, that bond, or form that bond between there's going to be a bond formed here. So this guy will now attack this and form a second bond here, and with that, this bond here will cleave and form a double bond here. Does that make sense? So when that happens, so this here is called betaine, okay? So when this guy occurs, when this bond cleaves, then you now form a triphenyl then you have your RC, R double bond, C. All right. So, of course, you're going to have the hydrogen and all. So, this is the way the mechanism proceeds, okay? I've forgotten this product, the name of this product. But this one is called triphenyl phosphine elide. Triphenyl phosphine elide. Is one of the intermediate products that is formed in the mechanism before the reaction, okay? So that is that. That is that about Wittig reaction. All right. So let's quickly talk about the physical and chemical properties of alkane. The video is already long. So what we'll do is I only explain a few. For the rest, I'll just give you the reactions so that we can, the video is already long. Let me just quickly explain the physical reaction. What are the physical reactions of alkene? Number one is the physical properties of alkene. From carbon 1 to carbon 4, that will be what? Gas. Then from carbon 5 to carbon 18, that will be what? Solids. Just the same way as we had it with that trend in alkene, alkanes rather. So then above C19, what do we have? Above C19, what do we have? And this one liquid rather. We have solids. Do you understand? So that means that their density increases as you go down the homologous series. Now, another thing with these guys is that their melting point also increases. But what happens is that an alkene, a particular alkene, we have a lower boiling point than its corresponding alkane. Why? Because the double bond is easy to break. Do you understand now? So a particular alkane, we have a lower boiling point than its corresponding alkane. For example, ethane, compare ethane and ethene. Even I can't remember that boiling point, but I do know that this guy is going to have a lower boiling point than this one, which have a higher boiling point than this one. Okay? Another thing with them is that I said their boiling point increases, right? By about 20 to 30 Kelvin as you go down the homologous series. Now, another thing with them is that they dissolve in non-polar solvent only. Non-polar solvent. Non-polar solvent. So that's that. I've already explained why in the video of Alkenes. So do well, because I don't want to stress the video again. So do well to see that video. I'll link it in the description. So that's that about that. Now let's go to the chemical properties. So now let me list the chemical properties. The chemical properties or the chemical reactions that we're going to see with alkenes are all or mostly first combustion, but mostly addition reactions. Okay, we're going to see mostly addition reactions. Now, with the addition reaction, I'm only going to explain one mechanism because that's the most important one they ask in exam, especially yes in exams here. So we have a few of them that I'm going to explain. Then we now have oxidation and polymerization. Okay, so with combustion reaction, what do you see? With combustion reaction, just reaction between what? Let me clean here too. Combustion reaction. I'm going to list the addition reactions, okay? Now the combustion reaction is just what? Our alkene, so let's say it was X here, HY, a particular HY, or here's HY. And what you will see is when you add it to oxygen, you add it with X plus Y over 4 oxygen, you will get carbon dioxide this side, that one. Excuse me, please. You get this guy, X CO2 and Y over 2H2O. Let's verify this. So we have C3H double D 6 plus, this will be 3 plus Y, which is 6 over 4 O2 to give X, that's 3 CO2 plus 6 over 2H2. So we have C3, H6 plus, now 2 here to 2 here 3, so we have 3 plus 3 over 2, that's 3 plus 1.5, that will be 4.5. That is 9 over 2 O2. I hope you understand what I did there. Alright. And we have 3 CO2 plus 3 H2O. Now what we'll now do is multiply through by 2. Okay? So multiply through by 2, we'll have C2C3H6 plus 9O2 to give by 2 6CO2 plus 6H2O. Let's see. 12 hydrogens. Oxygen is now 6 carbon. Oxygen 18. 6 plus 12. That's correct. So this is the general combustion reaction of alkenes. All right. Now under controlled oxidation also, another product is formed. Okay, so I'm going to talk about that in oxidation. There's the other reactions, okay? We have ozonolysis. So this also under controlled addition we get other products. So for example, ozonolysis. So that's what I'm going to explain. Ozonolysis. The other reactions I did not add here, okay? So for example here, under addition reaction, we're going to see halogenation. We are supposed to see halogenation, addition of this, then addition of hydrogen halide, okay? Then we are supposed to see hydrogenation itself, okay? Halogenation, hydrogen halide, hydrogenation, then Which other addition do we have? Hydration. Okay, addition of water. Yes, many addition reactions like that. We also have hydroboration. Now that I'm remembering them, hydroboration. I may not explain all of this. I might just give you their chemical formula. Epoxidation, and there's hydroboration, epoxidation, and blah blah blah, and yada yada yada. Okay, there are just many reactions like that. So we're going to be seeing. I'm going to explain all the mechanism there, but let me just show you the simple way it occurs. For addition reaction of alkenes, let's take this same alkene, this propene here. Now what will happen? This propene, I hope you know why. C3H6. Alright? Now, by the time you add, let's say chlorine, for example, on addition of chlorine, this takes place in presence of platinum or palladium or nickel catalyst. And I've already told you that with nickel, you will need a higher temperature and a higher pressure. The temperature is as high as 80 degrees Celsius and with high pressure, so with heat here. But the temperature with this one is lower, but we still, and the pressure is lower. So we call this one Sabatier-Sanderson's reduction, if you remember. What was I now saying? So if you add this to this, what will happen? You are going to get C, you know what you had initially was C H, like this. And this is what you had here. C1 to 3, H1 to 3, 4, 5, 6. Okay? So by the time you add chlorine, the chlorine will break this bond, and what will happen? There's going to be addition of chlorine to both ends of this guy. So what we have will become something like this. Chlorine here plus C, chlorine here, and H and CH, H. And I have told you that this is the anti-conformation, right? Anti-conformation. And I told you why. The syn conformation is less likely because of steric hindrance, steric disturbances. So what will happen is that they prefer the okay, this is not anti-periplanar, this is anti-position. Okay, it's not planar. I've told you that before. It's not planar. Now when they go in this position, there is less steric hindrance. And all substances want to attain a lower energy state. So this one has a lower potential energy than if the two Cl, for example, if it were like this. So this one will have a higher potential energy than what we first wrote. So it will not like this conformation. It will prefer a lower energy state. Do you understand now? So this is what you will get under addition of this guy. All right? Okay. So the next one we'll talk about is the addition of hydrogen halide. With addition of hydrogen halide too, now with addition of hydrogen halide, we now have what is called, the process here is called halogenation. This one is hydrohalogenation. This one is hydrogenation. This one is hydration. Okay? Halogenation because we're adding halogens. Hydrohalogenation because we're adding hydrogen halide. Hydrogenation because we're adding only hydrogen, which means we are reducing or reduction of that thing, of that alkene, for example. Then here, hydration. So let's talk about hydrohalogenation. Now, you should listen here. Hydrohalogenation, okay? That's addition of That's what? Addition of hydrogen halide. Now you should listen carefully here. We're talking about chemical properties, not physical. Now you should listen carefully here because we're going to talk about the Markovnikov's rule and the anti-Markovnikov rule. This is one of the most important aspects where they ask their questions. Okay? Now, we want to add that. So let me give you how it normally proceeds. So for example, let me still choose my propene, okay? Now what will happen if I add my hydrogen halide, for example? They are going to also add, now this one, the conformation is arbitrary. They can either add up like this, give you this. This is the new hydrogen that has been added to it. Is either they form this, which is the anti-conformation, or they form this. Our hydrogen is added and our Cl. Did you notice now that the conformation is arbitrary? Either they form the same conformation or the anti-conformation, that is in the opposite direction or in the same place. Do you understand? They are because there is no steric hindrance. This is a bulkier group or a relatively bulky group than hydrogen. Okay? Alright, so that's that on that. Now here's now the case. If we want to add, yes sir. If we want to add, now this is an asymmetrical, okay, this is an asymmetrical carbon, okay, this is an asymmetrical alkene rather. Now, if we want to add to a symmetrical alkene, the product is always the same. But if we want to add to an asymmetrical alkene like this, there are two possible products. Now, it's either we want to add to an asymmetrical alkene, the product is this and this. If you want to add to a symmetrical alkene, let's see, for example, butene. Now let's add HCl to it. Now this, we want to talk about the Markovnikov rule now. These are the only products that could be formed here, right? So with this is asymmetrical, right? So the asymmetrical products with asymmetrical alkenes, the product could be of two types. I'm trying to, if we can add Cl here and add Cl here. Okay, yes. So with asymmetrical alkene, the product is always the same. The product is always what? The same. But with a symmetrical alkene, what will happen? The Markovnikov product is formed. Markovnikov's product. Okay? Another way you might see people spell it is Markovnikov's. Okay? Again, I don't know the convention, maybe it's like British, American and all. Now, listen to this because we also have an anti-Markovnikov rule. Okay? Now, here, what will happen is that this guy is going to be added to this, right? Now, there are two ways it could be added. It's either the hydrogen here gets, oh, sorry. The asymmetrical alkene is the one that follows Markovnikov rule. Because here, whether you add hydrogen here or and add chlorine here, or add chlorine here and add hydrogen here, you are getting the same product. Okay? But with asymmetrical alkene, now what will happen? So let me clean this place. This is symmetric. With symmetrical alkene, what you have there is what you see. So whether it's anti or syn is the same thing. But with symmetrical alkene, that's what will happen. But with asymmetrical alkene, here's what will happen. Why is it asymmetrical first? Asymmetrical because across the double bond there are different groups. But with symmetrical alkene, you will see both two in that I wrote then, it had the same group across the double bond. Okay? So what do we have here? There are two products that can be formed from this reaction. Is either we have this, you know, this group is smaller than this group, right? This is the bulky group here. So Markovnikov now said that you should add the bulkier group to the most substituted again. Add the bulky group to the most substituted. So let me use another language. Is either you say you add the bulky group to the most substituted, or you say you add hydrogen to the carbon that has more hydrogen and add the halide to the one that has less hydrogen. So there are two possible positions for these two guys now. Is either you add hydrogen to this one and chlorine to this one, or add hydrogen to this one and chlorine to this one. Okay? So, but Markovnikov now said that the product you should form is add hydrogen to this one that has more hydrogen and add chlorine to this one that has chlorine. Do you understand now? This one that has less hydrogen. So what you will have is the Markovnikov product that you form is what looks like this. So this is our hydrogen that is added. Then here will be our chlorine. Does that make sense? I only chose the anti-conformation. I already showed you the conformation is arbitrary. Do you understand now? So this is the Markovnikov product. Why? Because the bulky group is added to this guy. Now, here is the reason. The reason is that this mechanism also it goes with, we call it an electrophilic addition. All of this, we call them electrophilic addition. And the reason is the same. Why are we adding the bulky group to the most substituted? The reason is because under this electrophilic addition also, we will also form a carbocation. So the carbocation that is formed is only stable with what? A more substituted carbon, right? A carbon that has more carbon around it. So before the attack of the electrophile, this is an electrophile, before the attack of the electrophile, what will happen? The carbocation has to be formed, so it is stable. It is only stable when it is what? More substituted. So this is what will happen in this case. Okay? Do you understand now? So what that means is that if I want to add to pentine, for example, pentene rather, for example. Yes, in fact, even is boots, but this is also anti. This is also asymmetric, right? Because the double bond, across the double bond, you don't have equal groups. If you have double bond here, then you have equal groups across the bond. But the double bond now is here. So you have 3 carbons here, 1 carbon here. So this is also what? Asymmetrical. So if you want to add across this double bond here, let's say I want to add HBr, for example. This one will be attached to what? To this, and this Br will be attached to this. Okay? That's the Markovnikov product. Now, what is now the anti-Markovnikov product? The anti-Markovnikov product says that in the presence of a peroxide, now it was proposed by Karask, so that's why it's called the Karask effect. Okay, it's called peroxide effect. It's called peroxide effect or the Karask effect. Karask, now there were 2 scientists that actually came together, Karask and Mayo. Okay, so we call it the Karask and Mayo effect. Now, So Markovnikov or Karask said that in the presence of a peroxide, what will happen is that the hydrogen, so this is Markovnikov that say now, if this occurred in the presence of a peroxide, what will happen is that this hydrogen will now be added to this one, and this one will now be added to this one. The reason being that what? Because of what? Bulky group 2 steric hindrance. Okay? So what will happen is that what you will form, the anti-Markovnikov product will be like this. Okay? And CH3. So this will be the anti-Markovnikov product in the presence of what? A peroxide, or known as Karask effect. So addition of hydrogen also. Addition of hydrogen takes place in the presence of this guy. So let's put that down. So addition of what now? Of hydrogen. What is it called? Hydrogenation. Okay. So now a question that is commonly asked is about hardening of oil. This is the process by which we harden oil. Okay. Hardening of oil takes this process. Okay. So you have an alkene, for example. In this case, I'm using propene. So if I want to add hydrogen to it, the process is called what? Hardening, right? No, for oil, only for oil, it's called hardening. Why? That's the process by which you use to change liquid oil into mayonnaise or margarine, okay? It hardens it. Why? Because oil has unsaturated hydrocarbons. That's why PUFA is one of the best oil for us, polyunsaturated fatty acids. So fatty acids, they are formed by what? It has the fatty acids. There are 3 backbones, right? There are 2. There's 1 backbone rather, and the alkenes on it, on the long chain. So those alkenes are the unsaturated. Okay, they are the reason for the unsaturation there. So when you're now adding it, that's why some butters they store in your body. But let's not get to that. Maybe we won't get to the biochemistry. I'm going to talk about it more. So here's what happens. In the presence of nickel catalyst, okay? Sorry. This one, halogenation that I said nickel catalyst, is not nickel catalyst. The catalyst for halogenation is CCl4. Because when I was forming, you remember when we reversed the process to get alkene, right? Or we get alkene. So when you now when you want to react, when you want to halogenate an alkene, the catalyst is methyl trichloride. So this guy, nickel catalyst, is this guy. Do you understand? So it now form an alkane. Okay, form an alkane. I'm just drawing this case. So now let's go. The next one is hydration. Okay, hydration takes place in the presence of. By the way, again, this halogenation, it could take place in the presence of it could be hydrohalogenation. Okay, that is what in the presence of water. No, hydrated. How do they call it? I've forgotten this name. It's bromine water that I will talk about now. Okay, bromine water. Now, bromine water. The color of bromine water is reddish brown. Okay, is this the test for saturation? Is the test for unsaturation. Okay, the reddish brown color changes from reddish brown to colorless. So we say that alkenes and alkynes decolorize bromine water. Alkenes or alkynes, which are the both unsaturated hydrocarbons that we have, they what? Decolorize bromine water. Please change that alkenes. The the catalyst that I wrote, CCl form. So this is how we form alkane and how we harden oil. Okay, and that makes sense. Don't worry, in the biochemistry, I'm going to explain why the oil becomes harder because of compactness, all right, because of the straightness and all right. You know when there's a kink, there's a bend. There's a double bond, there's a bend, a kink. All right, so that's that. Now, in under hydration, we form what? Alcohol in the presence of what? Acid. So let me just put that down because of the time. Plus H2O in the presence of acid, H2SO4, for example, at 180 degrees Celsius, just like what we did there. What will happen? We form alcohol. We just reverse the process of that thing. Okay. We also can use by product of there are two ways by which we can form alcohol. Okay. There's one other one that is called oxymercuration, demercuration. Now this one leads to a better yield of alcohol. Okay. Oxymercuration is just mercuric acetate is added to alkene. When it's added to alkene, then there is demercuration and then an alcohol is formed. Okay, that's the process. Mercuric acetate is added. Okay, mercuric acetate is just HgOC3. So this is added to an alkene. Then there is oxidation of this alkene, hydration of this alkene rather, and then alcohol is formed, and then there is demercuration. It's followed by demercuration. So that one leads to a higher yield of alcohol than this process here. Another thing they could ask you about hydration of alcohol is in the presence of an oxidizing agent, a good oxidizing agent, where you form this thing. Ethylene glycol is used as an antifreeze. Excuse me. So that's that. So I said we use ethylene glycol as an antifreeze. All right, so that's that. Now ozonolysis. Now let me just quickly show you this one. That's the simplest, ozonolysis. Now if I wanted to ozonolize this guy, the reaction, I'll tell you what the mechanism is, but I'll not do it with you. I just want to show you. When you add ozone to this guy in the presence of water and I think zinc, can't remember, you should just verify this, please. Verify this. This guy and what? Water and something. So when you ozonolize this, you form an intermediate product is called ozonide. Okay? Okay, I'm going to draw what that looks like, but let me show you how to draw it. When you have a particular alkene like this, and you want to ozonolize it, what you do is just, this ozonolysis I'm explaining now, ozonolysis, okay? What you want to do is just ozonolysis, that's breakage by ozone, right? So you want to break this bond and put O here and O here, okay? So whatever you have here is what you have, whatever you have is what you have there. So for example, if it's propane we are dealing with now in this case, when you break this bond, put O here, what do you have? On this side you have CH2O, right? And on this side we have CH O, right? That is C, H and double bond O. Does that make sense? And CH3. So this is the product of ozonolysis here. Right? So it forms an aldehyde. Okay, usually it can form aldehyde. Okay, my microphone is gone, so here's what I'll do. Let me just show you what happens here to become. So this is polymerization reaction. Subscribe to the channel. God bless you.